Next, we're going to talk about how to make inferences about a probability success parameter. In other words, we're going to be talking about how to construct confidence intervals and how to perform hypothesis tests for pi. There will be three different confidence interval types that we're going to be talking about, where the first one's referred to as a walled confidence interval. Walled confidence intervals are widely used throughout statistics, and the reason being is because they follow directly from our results from our maximum likelihood estimator. So in general, suppose we have a maximum likelihood estimator. We're going to call it theta hat. Think of this as a random variable. And based upon our previous discussion, we know that a maximum likelihood estimator like this has an approximate normal distribution for a large sample, where what we would expect theta hat to be on average, in other words, the mean of it, will be theta. And also it has a particular estimated variance associated with it, which is associated with the second derivatives of the log likelihood function. Now, based upon this result then, we could form this statistic, theta hat minus theta over the square root of this estimated variance of theta hat, and say that this has an approximate standard normal distribution. So this tilde with a dot on top of it means it has an approximate distribution. In this case, a standard normal. And again, this is for a large sample. Then what you saw in a introductory stat class before coming into this particular course is how we can take a result such as this and form a confidence interval with respect to our parameter of interest. So, just to review the technique that would be used. Since this quantity here has a standard normal distribution, I'm going to put it down here. And a standard normal distribution means then I can find particular quantiles from the standard normal distribution such that I know the probability that this statistic is somewhere in between these two quantiles has a particular value. So how about we find the alpha divided by 2 quantile from a standard normal, the 1 minus alpha divided by 2 quantile from a standard normal, and then put our statistic in the middle, and then find the corresponding probability, and that probability is approximately 1 minus alpha. Again, the approximate part there comes about because, again, this relies on a large sample. Now, just to make sure that you understand what this corresponding quantile from a standard normal distribution notation means, let's review that. In an introduction to statistics course, you would have seen some kind of notation very similar to this, but maybe not exactly the same as I'm using here. So let me go ahead and draw out a rough diagram of what a standard normal distribution looks like. So of course it's going to be centered at 0, symmetric about 0, even though unfortunately my drawing doesn't quite capture that symmetry. And I'm going to put z sub 1 minus alpha divided by 2 here. What this value on my, let's say my x-axis in my plot represents is that the area to the left underneath the curve is 1 minus alpha divided by 2. So equivalently, I could say that this is the, or actually let's think of this in the case of a 0.05 here. If I have 0.05, then that means I have 0.975 in that subscript. And so the area to this left of this quantile is 0.975 underneath this standard normal curve. This particular value ends up being 1.96. In other words, the quantile is 1.96. How could I find that quickly in R? I could use the Q norm function, Q standing for quantile. For the probability of being to the left of this quantile, I have 1 minus 0.05 divided by 2. I have a standard normal distribution, so I have mean equals 0, standard deviation, or SD, equal 1. Now, some people will refer to this instead as the 97.5 percentile from the standard normal distribution. I typically use instead 0.975 quantile. It's equivalent terminology. Now notice that this is the area to the left. And unfortunately in statistics we're not always consistent with this kind of notation. So in another class you might have saw something like this, where z sub 0.025, where 0.025 was to the right of this quantile, was positive 1.96 as well. We're going to not use that notation. Rather, we're always going to have in that subscript area there, the area to the left. Now, if I have z sub alpha divided by 2 here on this left-hand side there, and if I put alpha 0.05 in there, similar to what we just saw, I would have 0.025 in that subscript, and that represents now, I'm right over here, so the area to the left of negative 1.96 is 0.025. So the 0.025 quantile from a standard normal is negative 1.96. Okay, so we have this statistic. It's in the middle of two quantiles from our standard normal, and we know the probability of this statistic being within inside these two quantiles is approximately 1 minus alpha. Where does 1 minus alpha come from? Well, take alpha divided by 2, add it to 1 minus alpha divided by 2, you get 1 minus alpha. Okay. Now, what we can do is actually do some algebra. And we can then rewrite this expression so that alpha is only in the middle. And then we have theta hat minus the value from the standard normal, that quantile, times that square root of the estimated variance. And then on the right side, we have theta hat. We have a value from that standard normal, the 1 minus alpha divided by 2 quantile there. And then we have the square root of the estimated variance of theta hat, just through using some algebra. Do note that this right here is actually equivalent to a negative z alpha divided by 2 because of the symmetry property of a standard normal. Again, if we take a look at this just to make sure it's clear, do a little bit of erasing here. Oops, that's not the eraser. So if I have negative 1.96 here, positive 1.96 there, I get 0.025 in the tail of the distribution there, 0.025 in the tail of the distribution there, and 0.95 in the middle. Okay. So I have this approximate probability here that this inequality will work out. That's great, because now I have that parameter in the middle, and I have some certainty with regards to this probability statement. Now, if I take this quantity outside the probability statement and replace the random variables, which would be theta hat and the estimated variance of theta hat, replace them with what their observed values would be, then I can state then my 1 minus alpha times 100% walled confidence interval for theta. So again, depending upon your introductory statistics course, you may not have seen this formal notation here, 1 minus alpha times 100%. Just think of it this way: if alpha is 0.05, what we have then is 1 minus 0.05, let me put alpha there, 1 minus 0.05 times 100, or in other words, 95. And so that's just a general notation that people often use. So this is my walled confidence interval here. It's named after Wald, who came up with this result regarding what happens for a large sample for these maximum likelihood estimators. So now let's put this walled confidence interval, this general format, into use for us to find a confidence interval for pi, the probability of success parameter. Again, we saw that pi hat, which of course was w divided by n, number of successes over the number of trials, is our maximum likelihood estimator. And if we think of that as an actual random variable, we can go ahead and find then the corresponding walled confidence interval for it, and then replace the random variables with their observed values. And here is our walled confidence interval. So before we had theta hat, before inside the square root sign, we had the estimated variance of theta hat. And here's my walled confidence interval. Now, if I wanted to write this in a little bit of a, let's say, shorthand notation, notice how I have a minus there. I have, that actually should be a plus there. I'm taking my pi hat minus a quantity, pi hat plus the quantity, plus a quantity, and this quantity is always the same, so I could rewrite it like this here. Okay, so there's my walled confidence interval. And typically, in any introductory statistics course, which again is the prerequisite for a categorical data analysis course, you would actually learn this particular interval. Unfortunately, there are some problems with this interval that probably a lot of you have never learned about before. And we're going to be spending some time in these notes and also in some later notes talking about what are the problems associated with this. First of all, let me talk about two of the problems associated with this interval. Look what happens if pi hat is equal to 0 or 1. So I observe 0 successes out of n trials, or maybe n successes out of n trials. Look what happens. Now, if pi hat, suppose pi hat was 0, I would get 0 plus or minus the value for my standard normal times the square root of 0 times 1 minus 0 over n. So this whole quantity here then becomes 0. So essentially my interval is 0 plus or minus 0. Well, that's not a really good interval. If pi hat then is equal to 1, my interval is 1 plus or minus 0 again. Because why? Notice I have a 1 there. I would have a 1 minus 1 there. That becomes a 0. So this interval will not be very informative at all. So that's one problem. Another problem is that, unfortunately, the lower bound for this interval could be less than 1. Could be less than 0. The upper bound could be greater than 1. Well, why is that a problem? Well, of course, pi itself is a probability. It's a probability of success. It needs to be between 0 and 1. And so it doesn't make sense to have an interval such as, let's say, negative 0.05 as the lower bound and a positive 0.1 as an upper bound. That negative 0.05 to 0 part there, that makes no sense at all. And so that's another problem with this interval. And we'll be looking at some other intervals very shortly that don't have these kinds of problems. Okay, so let's take a look at how we can go ahead and calculate this walled interval. Suppose we go back to our field goal kicking example, and let's say I went out to the football stadium and I kicked 10 field goals, all done under similar circumstances, and I made 4 of those field goals. Then, excuse me, let me get my pen back out here. There we go. Then let's say I want to find a 95% confidence interval for pi. So in this particular case, pi hat would be 4 over 10 or 0.4. So wherever I saw pi hat before in my expression for the interval, I replace it with 0.4. My 0.05, the 0.975 quantile from a standard normal is 1.96 as we saw before. And so if I do all the math, I get 0.0964 to 0.7036 as my 95% interval. Let's take a look at how we can actually do this calculation in R. And this obviously is a very simple calculation, but this is especially helpful to look at how we can do this in R for those of you who maybe do not have a whole lot of experience with R to begin with. Okay. So here's my corresponding program that we're going to be looking at. It's called CI pi.r, or confidence interval pi.r. And so the first thing I'm going to do is create an object called w that's going to have the number of successes. Create an object called n that has the number of trials. I'm going to set my alpha value, and then I'm going to find pi hat. So let me go ahead and run that code by selecting the R send button. And so if I go ahead and go over to my R console window, I can see that indeed W does have a 4 value. Let's go ahead and type pi hat, and I got 0.4 there. Now, what I need to do next is essentially program into R my equation that we saw for that walled interval. And so the first thing I'm going to do is find that variance expression. In other words, the estimated variance of pi hat. That is pi hat times 1 minus pi hat divided by n. We found that in a previous set of notes. So I'm going to go ahead and run that segment of code. And let's just take a look at this. And there's my corresponding variance. So it will be 0.4 times 0.6 divided by 10. Now to find my lower bound for my confidence interval, I can take my pi hat, subtract off that quantile from a standard normal, that 1 minus alpha divided by 2 quantile, just for emphasis, even though, well, excuse me, just for emphasis, I decided to put mean equals 0 there, SD equal 1, because we are working with the standard normal. If I wanted to, I could have actually done without it, because that happens to be the default. Then I take this times square root of the var.walled. That's going to be my lower bound. My upper bound is exactly the same, but now I put plus there. I put the results into an object called upper there. Notice my lower bound is called lower. So let me go ahead and do this. And if I type lower, there's the lower bound that we had before. If I type upper, there's my upper bound as before. Maybe I might want to display this kind of nicely by putting this all into a data frame. So I can use the data.frame function to combine these two results. And here we have it. If I want to, I can make it even look nicer by doing some rounding, because we don't need to know what the like the seventh digit is after the decimal. So I can use the round function in R to do this, where I specify the number of digits I want to round to. And now this looks a lot nicer. Okay. Let me come back to my notes here. Now we can do some of these calculations a little bit quicker by taking advantage of how R works with vectors of information. In other words, you can think of a vector as let's say a group of numbers together. If you haven't seen the mathematical definition of it before, if you have seen the mathematical definition, use that. Essentially, that's what a vector is in R. There are actually small differences. And so what I'm going to do next let me restate this. I want to combine these two lines of code that you see on your screen that I'm highlighting. And the way to do that is I take pi hat plus, I'm going to take it plus a negative 1.96 and a positive 1.96. And how do I get both of them exactly the same time? Well, I can use my qnorm function, where I combine together, or what R would officially call concatenate together, alpha divided by 2 and 1 minus alpha divided by 2. So let me just highlight that just to show you that indeed that's what I'm doing here. Okay, so that's how I get my 0.025. I get 0.975. I use the symmetry property of the standard normal distribution, so that's how I got negative 1.96 and a positive 1.96. So R automatically does basically applies this qnorm function to both of these numerical values of interest. Okay, then I take it times the square root of the var.walled again. Now look what happens here. So I have on the left here with qnorm, I have something that has 2 elements in it, a vector with 2 elements. On the right, I just have something that's just one particular value that we saw before. So how does R behave then? Well, simply what it does, it takes the square root of the var.walled multiplied by negative 1.96, and it gives you negative 0.3. Then what r does, it takes the square root of var.wald again, multiplies it by positive 1.96, and it gives you 0.3036. And so what r does then, it produces in the end a vector that has a length of 2. It has 2 elements in it. Then, if I take pi hat, which again is just one value, I'm adding then this thing that has 2 elements in it. Look what happens. R simply takes pi hat plus that first element, and then pi hat plus the second element, and then returns our interval of interest. So notice how I was able to combine then 2 lines of code with 1 line of code by taking advantage of how R does calculations on vectors of information. We'll see many examples of that throughout this course, throughout my book. Okay, let me come back to my notes again. Now, let's talk about what would be then let's say the official interpretation of this interval. So in the course itself, you're going to have many times where I say interpret the interval. You can use one of these 2 interpretations if you would like, and just modify it for the needs of the actual data problem of it itself. So I could say, well, with 95% confidence, the true probability of success is between about 0.0964 and 0.7036. Okay, again, we're finding a 95% confidence interval, so that's why I use confidence there. An alternative interpretation is as follows. The 95% confidence interval is, as shown there, and we would expect that 95% of all similarly constructed intervals to contain pi. This is a type of interpretation that's often taught in a mathematical statistics course because it emphasizes what a confidence interval actually means or what it's doing. And this is based upon how the inferences are being made here. We are using what's called a frequentist-based inference method. In other words, if I were to go out and kick 10 field goals, calculate an interval, go out and kick another 10 intervals, calculate the interval. Suppose I did this many times, maybe let's say 1,000 times. Then I would expect 950 of those intervals to contain whatever that one true value of pi is. So notice how I repeated this process frequently. That's where the name frequentist comes from. So you can use either of those types of interpretations. Now, unfortunately, here are some incorrect interpretations that sometimes I will see when I teach an introductory statistics course. Please do not use these kinds of interpretations. I put them here as basically a review or a reminder of what is incorrect. Okay, first of all, the probability that pi is between 0.0964 and 0.7036 is 95%. That is actually incorrect. Now you might be wondering, well, wait a second. Let's take a look back at some of these expressions that you were given before. Okay, let me do some erasing. And let me just put in, we're going to put pi here, pi here, pi here, to put it in the context of what we've been doing. Okay. Before I know what pi is, before I go out and take my sample, I can still define what pi hat is. I know it's a random variable. It's a random variable that has, for a large sample, a normal distribution. Since it has a probability distribution with it, I can make probability statements about it. Okay? So it is correct to say something like this. Now, in our particular example, though, we observed that pi hat was 0.4. So let me rewrite this. Let's see, that's 0.4, 0.6, 10. Oops, that should be 0.4 times 0.6. Sorry, I'm kind of running out of room here. Okay. Once you replace that random variable with what it is observed to be, we have no unknowns anymore. We know that pi hat is 0.4. So I can't say that 0.4 has a normal distribution anymore. And so there actually are no random variables here. So this probability itself is either 0 or 1. Either pi is in the interval or it's not. So that's why we cannot say this interval has a 95% probability. This is one of the most difficult concepts for students to understand from an introductory stat course. And if you are having difficulty understanding that, please ask during our course or come talk to me, and I'll do a different approach to explain this. Another incorrect interpretation is 95% of the time pi is between 0.0964 and 0.7036. That is incorrect. There is one pi out there. So we can't really say 95% of the time pi is between this. Either it is or isn't, 0 or 1. The 95% confidence interval is 0.9064 to 0.7036. We would expect that 95% of all pi values to be within these limits. Again, this is an incorrect interpretation that I sometimes encounter in an introductory stat course for this or other kinds of problems. This is incorrect. Pi, there's one value of pi out there. There isn't like millions and millions of pi's. There's one probability of success parameter. And so it doesn't make sense to say that 95% of all pi values are within the interval limits. So be very careful on these interpretations. Note that if you use one of these interpretations, you cannot go wrong. One other little thing I want to mention that's not in the notes is that we could rewrite this interval if we wanted to as parentheses 0.0964 comma 0.7036 end parentheses. It's just a nice little bit easier way to write confidence intervals, and then that's fine as well, as long as we know what the parameter of interest is. Okay. So I got really happy with writing these notes, I guess you could say, and I put 3 exclamation marks there because what I'm going to be talking about is very important here. So this interval works if the sample size is large. Well, what do I mean works? It means that I do truly have, if I were to go out and take a sample, calculate the interval, go out and take another sample, calculate the interval. Suppose I do this many, many times, I would expect 95% of all those intervals to contain the one true value of pi. That works out if I had a large sample. The problem is our sample size is only 10 here. And so we're using this normal distribution when maybe it's questionable, in fact it is questionable, whether or not truly, to begin with, if pi hat, if we think of that as a random variable, truly has a normal distribution to it. And so then this leads them to the second point here, is that the discreteness of the binomial distribution often makes the normal approximation work poorly, even with large samples too. Actually, let me back up to this one. Excuse me here. So if n is equal to 10, that means that pi hat can be 0, it can be 0.1, it can be 0.9, it can be all the way up to 1.0. In fact, there are only 11 values with it. So pi hat has only 11 different values. But we're using a normal distribution, which is for a continuous random variable, to represent probabilities associated with pi hat. So hopefully you can see that, oh, okay, that's where the problem is that pi hat essentially has a discrete probability distribution in actuality, but we're approximating it with a continuous random variable. So even with a large sample, at times, that approximation doesn't work well. So what is the end result? Why is this truly a problem? Well, the end result is that the confidence interval, a walled confidence interval actually in general, in many situations, including this one, the confidence interval is what's referred to as a liberal interval, meaning that if I state the confidence level being 95%, that truly true confidence level, though, what it truly should be, what it truly is actually something less than that. It might be 90%, 85%, or even less for this particular walled confidence interval for pi. And so hopefully you can see then that that's the problem. Because if I state I have a 95% confidence interval, I want it truly to be 95%. And then if instead it's actually, let's say, 80%, that's a big problem. So whenever the true confidence level, and we'll actually have a whole subsection of the notes on this that explains this further. Whenever the true confidence level is less than the stated value, you have what's called a liberal interval. And so you might be worrying, well, what happens if it's higher than the stated value? That seems like that's a good property. And yes, it can be a good property. And when that happens, though, you have what's referred to as a conservative interval. Again, we'll talk about this more coming up. We'll actually show that indeed that a walled confidence interval for this situation is a liberal interval. So because of these problems, it's actually the problems with the walled confidence interval here for pi. It's actually kind of surprising that this walled confidence interval is still probably the most often taught confidence interval for pi in an introductory stat course. And there's been a lot of research done about, well, could we do better? Could we get a confidence interval that is closer to 95% if alpha was 0.05? And the answer is yes. And like I said, there's been a lot of research on it, a nice paper that summarizes some of the research. There's been a little bit of research done since this paper, but still probably the best paper out there is this Brown et al. Paper. And we're going to look at some of their recommendations and my corresponding comments about those recommendations here about what other intervals should be used instead of a walled interval. So they recommend using a what's called a Wilson interval. It was developed a long time ago by a guy by the name of Wilson. And this is what the interval looks like. Rather than starting with pi hat, they put pi tilde there instead, where pi tilde essentially is just an adjusted estimate of pi. So I have my number of successes again, plus here's my adjustment in the numerator. So I have the 1 minus alpha divided by 2 quantile from a standard normal. I square it. So if I have 0.05, I would take 1.96 squared. And then I divide that whole thing, that 1.96 squared, I divide it by 2. Again, think of order of operations of what you'll learn in an algebra class. And then the denominator, rather than only having the number of trials, I take my number of trials plus then this quantile squared once again. Well, that's my, let's say, adjusted estimate of pi rather than using pi hat. Then I have some other parts here. I had the quantile as what we saw before, but now I'm going to take the square root of my sample size, or number of trials, divide by, again, number of trials plus then this quantile squared. Then I take this all times the square root of my regular pi hat times 1 minus pi hat. Then I have my quantile squared divided by 4n. So this is kind of a weird equation, you could say, for this expression. So how does this actually come about? Well, what we can do is relate this to doing a hypothesis test for pi. And again, in an introductory stat course, prerequisite for this course, I expect that you've done this before. So maybe I might be interested in determining, is my my true probability of success for me kicking field goals, is it equal to 0.5 or not? And so I could do a hypothesis test for that. And what you'll learn in an introductory stat course is that this is the particular statistic that you would use in this situation. You take pi hat minus a hypothesized value of pi, maybe like 0.5, divided by the square root of pi 0 times 1 minus pi 0 over n. Pi 0, again, is the hypothesized value of pi. I'm going to call this a statistic. I'm going to call it z sub s. You'll see why it's called that in a little bit. And then the way that the interval then is found is that take this statistic And we know that this statistic ends up actually having an approximate standard normal distribution. So again, I could have a lower quantile, an upper quantile associated with it with a certain probability that you would expect the statistic to fall within there. Take this expression here and focus on this part, solve for pi 0. Then focus on this part, solve for pi 0, and you get the upper and lower limits, respectively, for pi 0. What this ends up being is that you have to use the quadratic equation to do this, to make this, to solve for it. I will not ask you in this class to actually do the derivation. You can just take my word for it that this is indeed how it's done. In my book, there's actually an exercise corresponding to this. In my class, I often will also provide some information on my course website that shows how the derivation is done for those of you who are interested in the mathematical details. Now, this whole idea of using a test statistic that you would normally use for a hypothesis test and turning it into a confidence interval is called inverting the tests. Just some terminology that if you take a mathematical statistics course, often you learn about. Okay. So we'll look at how to apply this equation shortly. The second interval is a little bit easier to find. It's called the Agresti-Cool interval, named after Alan Agresti and Brent Cool. Hopefully at some point in my life I'll have a builder interval. I guess I'm still working on getting one of those. But what Agresti and Cool said was this. How about we start with that adjusted estimator of pi once again, just like what we did with the Wilson interval. And we basically form a wall-like interval where wherever we saw pi hat, we replace it with a pi tilde. And we also make a small adjustment to the denominator here in that square root for that variance part. Okay. So it's essentially a walled interval with adjusted estimate for pi. And you can think of it this way. Let's look at the expression for pi tilde again. What we are actually essentially doing here, sorry, my eraser's not always working. Hold on a second. What we're essentially doing here is we are looking at the number of successes and adding an adjustment to the number of successes. We are looking at the number of trials and adding an adjustment for the number of trials. Now look what happens if alpha was actually 0.05. Then this z sub 1 minus alpha divided by 2 becomes 1.96. I square it, and I get approximately 4. And so what you can think of this then as this. When alpha is 0.05, I'm essentially adding 2 successes and 2 failures to my data. So notice this 4 here is 2 plus 2. So there's my 2 extra successes. So you have some kind of an intuitive understanding of how this adjustment is actually applied there. Now, why would we want to apply this kind of adjustment? Well, hopefully you remember from a few minutes ago, I said that this walled confidence interval has problems when you have, let's say, a pi hat that ends up being close to 0 or close to 1. You could, for example, get a negative lower limit when pi hat's close to 0. You get a lower limit, an upper limit that's greater than 1 when pi hat's close to 1. And so what this adjustment factor or adjustment does here, it basically moves my estimate for pi away from 0 or away from 1. And so on your own, what you should do is take a look at, well, what if, let's say, what if I have n equal 10 and I have n equal 10 and I have w equal 1. Take a look at what pi hat is. take a look at what pi tilde is. And you're going to see pi tilde is a little bit higher than that. It's moving things away from away from 0. Think about how that is going to then affect my lower limit of the confidence interval. It's going to move it a little bit greater than what it would have been normally. In a similar manner, suppose w is equal to 9. Look at what happens with pi hat. Look what happens with pi tilde. This pi tilde will be a little bit now lower than pi hat. So it's moving away our estimate from 1 where we start this interval calculation. So both the Wilson interval and the Agresti-Cool interval are better than the Wald interval. Why? Because the confidence level that I state with it, like 95% confidence, the actual true confidence level will actually be much closer, typically, than to the stated confidence level than what we had with the Wald. So I feel better then, you could say, that when I state 95% confidence, that truly we're somewhere near that 95% with the Wilson or the Agresti-Cool, where with the Wald interval, I'd be very worried. There will be one more confidence interval that we look at corresponding for pi, called the Klopper-Pearson interval. We'll talk about that a little bit later. Now, Brown et al. In their paper, they say, well, if your sample size is less than 40, use the Wilson. If your sample size is greater than 40, in terms of the number of trials, you can use the Agresti-Cool or Wilson. I don't think that's really necessary to make that distinction. Either Wilson or Agresti-Cool will be fine. They also talk about another interval that they recommend called the Jeffreys-Pryor interval. This uses a different paradigm for inference known as Bayesian inference. And so this isn't actually a confidence interval, but rather a credible interval. Typically, my regular way that I teach this particular course is I don't talk about Bayesian inference. However, there are some semesters where I will actually do whole sections on it. In fact, there's a whole section on it in my book if you want to know more about it. And lastly, for very extreme values of pi, something that's important to understand is that the Wilson interval can be very liberal, meaning that the true confidence level is actually a lot less than, let's say, 95%. The Agresti-Cool, though, an advantage is it will be conservative. I'd rather have a conservative interval than a liberal interval if I had to choose. I'd rather just be right at, let's say, 95% if I can be. And so that's something to think about. There are some adjustments that people have come up with for the Wilson interval to kind of correct the problem. The problem is that, or the issue is that unfortunately this adjustment or the correction is not directly programmed into an R function that we will use. So that's why I typically don't talk about it. Okay, so let's talk about how we can do some of these calculations then. So let's begin with the Agresti-Cool interval because it's a little bit easier to do the calculation. The first thing that we're going to do is we're going to find this pi tilde. And so what I need to do now is transform this equation that we saw into a form that R can understand. So I have my W. I add to it then this value for my standard normal that is squared. Then that whole quantity is divided by 2 using proper order of operations that you will learn about in algebra class. Then I divide by n plus that value from the standard normal squared. So let me go ahead and do the calculation here. I get 0.43. Notice how that's a little bit higher than the 0.4 that we got before for pi hat. Then what I can do is I can find my corresponding variance that we use with the Agresti-Cool. So I take pi tilde times 1 minus pi tilde rather than using the pi hat that we saw before. And since we're essentially adding, in this case, 4 more trials to my data, I take n plus then this quantile for my standard normal squared. So let me go ahead and do that. You can see here is my new variance that I just calculated. Then I can take my pi tilde just like what we did with the walled interval, take my pi tilde plus then the two values for my standard normal times the square root of that estimated variance. I round this to 4 decimal places, and here's my interval. This is different from what we had before. Let me actually show you what we had before again. So we can see how this interval was actually moved a little bit farther away from that bottom possible value of 0 for this aggressive cool. So let's also talk about how to do the Wilson interval then. I start with my pi tilde again, and then I just need to program in into R the corresponding equations that we saw. It's a little bit more complicated, but it uses the same concept. So because of that, I'm going to let you take a look at the exact details on your own. Remember though, you can, let's say, highlight portions of the code within inside the Wilson interval calculation to see what actually occurs. And so then my Wilson interval ends up being 0.1682 to 0.6873. Notice how similar that is to the Agresti cool interval. That's one reason why I don't really make a big deal about using one or the other. But again, it is somewhat different than what we saw for the walled interval. Okay, let me get back to my notes. So something that is important to discuss here is that, how useful would these confidence intervals actually be in actual application? So let's say that you work for a football team, and the coach for the football team says, "Hey, give me the 95% confidence interval for this this field goal kicker. I want to know, what his probability of success would be for a particular field goal." And if you told the coach, "Oh, I think it's between 0.1671 and 0.6884, the coach will be saying, "Well, wait a second, that's kind of wide there. That doesn't help me a whole lot." And in fact, for this particular problem, since we had such a low sample size, indeed, that is an issue. This interval is quite wide. In other applications, maybe having this wide of an interval wouldn't be as big of a problem, but at least for football in this particular case, I think this is a little bit wider than definitely what we would like. Now, there are easier ways to do some of these calculations. So what you'll see in my book, what you'll see in my course is that sometimes I will show you, let's say, a harder way to do something first, because I want you to see how the equations that are involved, how they all work out. This is an example of one of these cases. There's actually an easier way to do this. Somebody's actually constructed a function that automatically does these calculations. So there is a package that you can download and install, similar to what you saw in Appendix A and the corresponding notes with it, called there's a package called Binom that was written by some R users that contains a function called binom.confint that does these calculations automatically. So if I download that into R, I install it, and then if I say library binom and then use their function binom.confint, the first argument is x, which corresponds to what we use as w in our notation, the number of successes. The next argument is the number of trials, n. I can state my confidence level with conf.level. And then what kind of confidence interval do I want? Well, here I just decided, let's just show you all, just indeed show you that there's been a lot of research done. There's been a lot of different confidence intervals that have been proposed. And unfortunately, that did not come up correctly. I thought I had installed this on my computer, but obviously I did not. So here is a quick little introduction to installing this. So there's a number of different ways you can install a package. I decided to do the quickest way here, called install.packages, and then in parentheses I put the package name. And so what R is going to do is go out to the internet and go out to one of the R web servers out there, download the package and install it. And indeed, it did work out. So now I can say library binom and then use the binom.confint function, and voila, there I get my corresponding results. So you see here first shown aggressively cool. And in fact, that lower and upper limit is exactly what we had before. You can see the very last one, Wilson, which we had before. And then lastly here, you see something called asymptotic. This is the walled interval. Why does this name come about? Well, remember, we talked about in a previous set of notes about how for a large sample, the maximum likelihood estimator has a normal distribution. And some people would say instead that, well, theta hat asymptotically has a normal distribution associated with it. And so that's where the name comes from. So the asymptotic label here corresponds to our walled interval. This concludes the set of notes here on 3 confidence intervals for pi.